Hey everyone! Welcome back to the channel. Today, we're going to break down one of the most important and powerful data structures in computer science, hash tables. If you've ever wondered how fast lookups work behind the scenes in programming, or how dictionaries, maps, and sets achieve lightning-fast speed, then this video is for you. By the end of this video, you'll understand what a hash table is, how hashing works, how collisions are handled, how to implement a hash table in Java, and why hash tables are so efficient. So sit back, relax, and let's dive in. Section 1. What is a hash table? A hash table is a collection of key-value pairs. Each entry in the table has two parts. A key, which must be unique. A value, which is the data you want to associate with that key. Think of it like a big filing cabinet where each drawer has a label, and inside the drawer, you store a file. Here's a simple real-life example. Imagine you're a teacher managing student data. Each student has a unique student ID, that's your key. A name, that's your value. In Java, you could represent this like integer student id, string student, name. So, if student ID 100 corresponds to SpongeBob, you can look up 100 anytime and instantly get SpongeBob without scanning through every other student. This is where the power of hash tables comes in, speed. Section 2. How hashing works. So, how does a hash table know where to put each key-value pair? This is where the hash function comes into play. A hash function takes a key as input and generates an integer called a hash code. For example, key equals 100 hash equals 100 key equals 123 hash equals 123 but a hash table usually has limited capacity. Suppose our table has 10 buckets. We can calculate the index using the modulus operator. Index equals hash percent table, size. So, 100% 10 equals 0 SpongeBob goes to index 0 123% 10 equals 3 Patrick goes to index 3 this way. The hash function maps each key to a specific bucket inside the hash table. It's like assigning each file to a drawer based on a formula, fast and organized. Section 3. Collisions and chaining. But here's the tricky part. What happens if two different keys hash to the same index? This is called a collision. For example, Patrick's key index 0 Sandy's key index 0 2 people, 1 drawer. How do we handle that? The most common way is called chaining. In chaining, each bucket is actually a linked list. If the bucket already has one entry, we attach the new entry to the next node in that list. So if both Patrick and Sandy map to index 0, the bucket at index 0 will have a linked list containing both entries. When we want to find a key, we go to the correct bucket, walk through the linked list, find the matching key and return its value. This allows multiple entries to exist in the same bucket without losing data. Section 4. Implementing a hash table in Java. Now let's implement this in Java to see it in action. Java provides a built-in hashtable class. Import java.util.hashtable, hashtable integer, string table equals new hashtable here. Integer is the key. String is the value. Let's add some students. Table.put 100, SpongeBob, table.put 123, Patrick, table.put 321, Sandy, table.put 555, Squidward, table.put 777, Gary. To access a value by key, system.out.println table.get 100, / output, SpongeBob. To iterate over all key value pairs. 4. Integer key, table.keyset, system.out.println key plus / t plus table.get key. To remove a key value pair. Table.remove 777, / removes Gary. That's how simple and clean it is to use hash tables in Java. Section 5. Hash codes and index calculation. Under the hood, each key has a hash code. For integers, the hash code is usually the number itself. For strings, the hash code is calculated based on the ASCII values of characters in the string. For example, ABC hash code based on A, B, and C. Then, index equals hash percent table size. Each index is also called a bucket. If multiple entries land in the same bucket, we store them in a linked list, chaining. Increasing the table size reduces the chance of collisions, but it also uses more memory. So, finding the right balance between memory usage and performance is important in designing efficient hash tables. Section 6. Hash table complexity and benefits. Let's talk about why hash tables are so powerful. Advantages of hash tables. Extremely fast insertion, lookup, and deletion. Great for handling large datasets. Keys can be of various types, numbers, strings, objects, with proper hash functions. Time complexity. Best case, 01, constant time, no collision. Average case, 01, with good hashing, collisions are rare. Worst case, ON, when all entries end up in one bucket, a long linked list still, with a good hash function and a reasonable table size. Hash tables are one of the fastest data structures out there. Section 7, Recap and Wrap Up. Let's quickly summarize what we've learned. A hash table stores data as key-value pairs, allowing quick access by key. Hashing maps each key to a specific bucket using a hash function. Collisions happen when multiple keys map to the same bucket. We handle them with chaining, using linked lists. In Java, the hashtable class makes it easy to store and retrieve data. Hash tables offer 01 average time complexity for insertion, deletion, and lookup. Hash tables are everywhere, in databases, caches, programming language dictionaries, and even behind the scenes in many frameworks you use daily. If you want a copy of my notes or code examples, I'll drop them in the comments below. Outro, call to action, and that's it for today's lesson on hash tables. If you found this video helpful, give it a thumbs up. Drop a comment if you have any questions. And don't forget to subscribe for more easy to understand programming tutorials. Thanks for watching, and I'll see you in the next video.